Hi, in today's video we'll be discussing the LM317. Get a good clear view of that. Yeah, it doesn't want to focus properly. There we go. LM317 as I promised, which is it's an adjustable voltage regulator. Well, it's going to be used as an adjustable voltage regulator, but I'll briefly cover the adjustable current regulator application on it, and I'll also explain why we're not going to be using that. Basically, it's a 3-terminal positive device. It basically ranges anywhere from 1.25 volts all the way up to around about 37 volts. Yeah, let's get some paperwork ready. Yeah, anyway, by the way, the LM337 is the negative counterpart, but I won't be discussing much of that unless there's a great call for it. But yeah, but the LM317 will be using the TO220 package in this case. They're rated about an amp to 1.5 amp maximum if you heat-sinked it properly, and the operating temperatures from about 0 to 125 Celsius ambient temperature, that is. And but yeah, there's other little bits of information history about the LM31. Now, the LM317, it was invented in 1970 by Robert J. Weidler. He was working at National Semiconductors at the time. Unfortunately, he's no longer with us. He died in 1991 at the young age of 53. But, the great guy. This picture here, sitting over, standing over a workbench, is actually artwork from the LM10. This picture dates back to 1977, and yeah. So that's so he's the inventor of that. Here we have the pin out of the LM317. Pin 1 on the left we have the adjust pin. Pin 2 in the middle we have pin. And pin 3 on the right we have the input pin. Basically the input pin goes to your main input voltage, obviously, and output is where your output comes, and the circuitry involved in selecting the voltage level or current level all centers around the adjust pin. The basic specs of the 317 is the input ranges from about 3 volts to 3 volts to 40 volts to get your decent range out. Anything higher than that will definitely damage the 317. Now the output range goes from 1.25 volts, which is because of the internal voltage reference. It goes from 1.25 volts all the way up to 37. There is a bit of a dropout of about 3 volts, more or less 2-3 volts, depends on the voltage range, which you'll see a bit in the lab video, the bench video, which I'll show you. The operation will ambient temperatures 0 degrees to 125 degrees Celsius, but more current you put into the device, obviously that'll add on top of that, and it does get quite high if it's a lot of current. They are stated to handle about 1.5 amp when the correctly dissipated with the correct heatsink and fans, whatever. But in the TO220 package like this, I wouldn't like to get it anywhere near an amp, because it'll get pretty hot. If you want to do something like 1.5 amps, something, I'd suggest using the TO3 case, which is the big fat transistor package. Here we have a basic voltage regulation circuit and some formulas showing you how to calculate the different resistors in the circuit. Now, after this slide, we'll go to the workbench and see this in action. Basically, there's supposed to be a capacitor on the output, smoothing the output, but I didn't include it in this diagram, but it is used on most circuits. But basically, the formulas here, if you know your R1 and R2, then you can work out what voltage comes out. Alternatively, if you only know R1 and you want to know what you want to come out, then you can use that formula. And the same for the R2 formula, which I'll give a demonstration of that right now. So yeah, let's go straight to the bench and set up a simple circuit. Okay, I got the bench set up here now. What I have is the LM317 and a meter hooked up, and the power supply hooked up. It's actually set for 9 volts. I'll show you in a bit. Okay, what I've done is I used a calculation to work out. So yeah, I want to aim for 5 volts to come out of this circuit. So what I've done is I've fixed R1, in this case this one, to 1K to make it an easier one to remember. So basically, 1K for R1, 5 volts for the V out is what we're after. Okay, so let's have a look at this. So 1K, there we go. 5 minus 1.25 over 1.25. Okay, so we get a value of 3 kilo ohms for R2. So therefore I put 3 kilo ohms. So okay, so what I've done is I put 3 1K resistors in series. Going to ground as I stated here. Now this I actually have hooked up ready to be replaced to show you a variable version. But as it is right now, it's set as a fixed output of 5 volts. So let's flick on the switch. Okay, it says 9.1. I actually measured it as a 9 in the meter before. Okay, so now here's the output, 5.122. Now the accuracy of these resistors may be, maybe a little out. Same with the accuracy of my meter. So obviously we would tweak the value to make it better. But yeah, so using those values, this is what we got. So I'll just turn that off. And we'll have a look what happens when we put the pot in instead of the 3 volts, instead of the 3K resistance fixed. Okay, that's a 10 turn 10K pot. I don't know what it's set to right now, but let's have a look. See what happens here. Okay, so we're at 4 volts. So if I turn it, I can very accurately set to 5 volts if I want, or if I want to go down about, I can go down to 4 volts as well. Fortunately, I wouldn't be able to go down any further than 1.25 volts because of the reference set inside it. Okay, let's just just tweak something. There we go. Okay, so let's see what happens when I do that. Turn the pot all the way down. There. That pot is down as far as it will go. And it doesn't go any further down than that. Like I said, my meter's probably out of calibration. So let's go all the way up and see how far it goes up. Keep in mind the alligator clip fell off. Keep in mind the input voltage here is 9 volts. There we go, I've got 8.17 volts. Okay, let's just wind it down. So yeah. So that's the LM317 being used as a voltage regulator. I'm not getting any heat off that right now, thankfully, so I'm not drawing too much current. But yeah, we'll have a look at some calculations for that. Let's see what the voltage regulation to work well. So now let's explain the current regulation configuration. Now basically all you need is one resistor, which would be needed to set the current in the LM317. Basically the output current is limited by the voltage reference, which is 1.25 on the LM317 over the output resistance. But you have to keep in mind all the current is basically going to be flowing through the resistors, so it may need to be a higher wattage, and if it's a variable resistor, then you're going to have one with a higher wattage, and those things can be quite expensive, and it gets quite hot, and yeah, and it's not the most stable design, which is one reason why I don't use this kind of current regulation. But if you need a quick current regulator and a snap to like charge batteries or something, then this is usually the way. This also is used to power laser diodes to keep a constant current on those, to stop them burning out. Yeah, I've set this up for current regulation. There's not really much to it. Looks a bit convoluted, unfortunately, but basically that's the circuit we have. Okay, now in this case R1 is actually a 10 ohm 5 watt resistor I have. That's that there. And that goes out to low, but what I've actually done is I've got 0.1 ohm 5 watt resistor on there just to load it, and the meters and current measurements. Okay, so basically here's the formula for working out the current. So the voltage reference 1.25 volts. So basically if we put 1.25 ohms we get 1 amp hour. But in this case, so we've got so it's 1.25 volts over 10 ohm. So basically it's that divided by 10, so 0.125 amps or 125 milliamp. So that's the calculation. Let's let's see if that's true. Now the meter's still set at 9 volts, and I'm on the milliamp range, and let's give it a try. 124.3 milliamp. That's close enough. That's a good proof of concept that it actually works. As long as you got to be careful, because some of these can get quite hot. of a dodgy lead there. But yeah, I'm not really getting any heat dissipated, am I? No. That looks pretty good. So yeah. That's a proof of concept for the current regulation. Now, the problem is, yeah, this does need to sink quite a bit of current to make it work properly. So, so therefore, I won't be using this method for current regulation in the power supply. Yeah, the current voltage regulation circuits seem to go pretty well. The voltage circuit was a little out by the calculations, but I think that is mainly due to the calibration of my meter, which is not very good. Just expect for a cheap $30 eBay special from China. So no, don't get me wrong, it's not a bad test meter, but yeah. But yeah, the problem with the LM317, like I said, the 1.25 volt reference, it limits you on the low end. So like if I wanted to go, like if I wanted a nice 1 volt for an experiment, I couldn't do it with an LM317, unfortunately, due to that limitation. Which is one reason why I'm not using it. Another reason is the current limitation. I know you could probably, I know you can get bigger versions of it, but they get pretty hot at 1 amp. And this design, I always try and design for like a 2 amp system, just to keep it all, even and that, so it's there if you need it, so that this thing would get really hot and definitely die on us, unfortunately. And yeah, similar reason for the current regulation. It's a little limited in places, and the resistor to set the current needs to be like a bit of a hefty wattage, depending on how high you want it. And if it's about 2 amp, then you need a really hefty one, because it will get really hot, and I find that a little bit too difficult to handle. So yeah, but I have better ways around it, which I will be highlighting soon. And yeah, in the next video that would hopefully be coming up soon, we'll be doing some SPI experiments with the Arduino, and hopefully I'll rewrite the drivers for the MCP 3304 and MCP 4822, the ADC and DAC respectively, and I'll make all that open source as well. If you're looking for the code for the MCPs that I already did, you'll find them on my website, which I've linked below. And yeah, those videos will be up as soon as I can. Yeah, this one's been a bit delayed, unfortunately. Like I said, I've been overrun with school and stuff, but settling in, not much time afterwards, because I've come home, fallen asleep, and that. Today I actually did fall asleep for a little bit, but I'm back on my feet again doing the video. But yeah, basically that's the end of the LM317 video for now. If I find any more information, or I get enough feedback and desire for the LM337, then I'll record that and add that on in the next few episodes. But yeah, anyway, the power supply is slowly taking shape. The designs I've shown you now can be added in place of the 7805 voltage regulator that was shown in the previous linear video, which will then create your variable supply. And also, for those that have done the power supply conversion from an ATX to a bench supply, you can also use the LM317 circuit as a voltage varying device for your for the 12 volts line. And that way you got a decent, well, it's not decent, it's a usable variable supply that can be used. Okay, so I'm gonna wrap this up now and get editing it and hopefully have it out soon. So yeah, thanks for watching. Please like and subscribe if you haven't already, and I'll see you in the next video. Okay, goodbye.